Hello, and welcome to this video. This video is the second in a series that addresses the use of artificial intelligence in emergency management. This series deviates from the material contained in Chapter 8. The reason for this is because of the proliferation of artificial intelligence into many aspects of business and governmental operations. These operations include emergency management. Students should watch and study these videos as they prepare for the module quiz. Artificial intelligence is rapidly becoming an important tool in emergency management. From predicting where flooding may occur to analyzing satellite images after a hurricane, AI can help emergency managers process enormous amounts of information and make decisions faster, but not every artificial intelligence system operates in the same way. One important distinction involves open-source AI and closed-source AI. Each approach offers advantages, but each also has limitations. For emergency managers, understanding those differences is important because the best AI system may depend on the mission. This video examines open-source and closed-source AI, compares their strengths and weaknesses, and then explores how artificial intelligence can support all four phases of emergency management: mitigation, preparedness, response, and recovery. So, what is open-source AI? Generally, open-source AI refers to artificial intelligence technologies in which important components of the system are made available for others to inspect, use, modify, or build upon. In other words, the data and the systems used are available to others outside the organization that is using this data and systems. Exactly what is made available can vary considerably among AI systems. For emergency managers, the important concept is flexibility. Open approaches can allow organizations to adapt AI tools to their particular needs. A state emergency management agency, university, nonprofit organization, or local government might customize an AI application for hazards affecting its community. Open approaches can also support broad access to information and encourage experimentation and creativity. Imagine an emergency management agency developing an application to analyze wildfire risk. An open AI model could potentially be combined with weather information from the National Weather Service, vegetation data from county extension offices, historical fire records from various fire departments, GIS information from the U.S. Geological Survey, and local planning data. That flexibility can be extremely valuable. Open AI ecosystems may also allow developers and researchers to integrate newer information and specialized data sets. This can make them useful when emergency managers are dealing with rapidly changing conditions. However, flexibility does not automatically mean reliability. Open source AI is not without its challenges. One major concern is hallucination. An AI hallucination occurs when an artificial intelligence system produces information that sounds convincing but is incorrect, unsupported, or completely fabricated. Consider how dangerous this could become during an emergency. Imagine asking an AI system, "What shelters are currently operating in this county?" The system provides 3 locations. The answer looks professional. The addresses look reasonable. The information appears credible, but one of those shelters does not exist. Another closed several hours ago. And the third is outside the evacuation area. In a classroom exercise, incorrect information might only result in a wrong answer. However, during a disaster, incorrect information can affect human safety. A second challenge is misinformation. AI systems may encounter inaccurate information from websites, social media posts, outdated documents, rumors, or other questionable sources. If that information enters the decision-making process without proper verification, emergency managers may make decisions based on false assumptions. The third challenge is variable reliability. An AI system might perform extremely well on one task but poorly on another. It may summarize a weather report accurately but struggle to interpret local emergency procedures. This leads to an essential principle. AI-generated information should not automatically be treated as verified information. Human judgment, source verification, and professional expertise remain critical. Now, what is closed-source AI? Closed-source AI generally refers to systems whose underlying models, code, training processes, data, or other components are owned or otherwise controlled by an organization and are not fully available for outside inspection or modification. In other words, the data and system belong to or are controlled by the organization, and no one else may have access to them without the organization's permission. In the context of the report, closed systems emphasize qualities such as trusted data sets, accuracy, security, and consistency. Imagine an emergency management organization using an AI system specifically designed to analyze infrastructure damage. Instead of drawing from broad and potentially unreliable information, the system might operate using carefully selected data sets, validated engineering information, established agency procedures, and controlled information sources. The advantage is greater predictability. If an emergency manager needs an AI system to perform a specific operational task repeatedly, consistency may be more important than creativity. Security can also be an important consideration. Emergency management organizations frequently handle information involving critical infrastructure, government operations, resource locations, damage assessments, and other sensitive operational information. Organizations therefore need to consider not simply what an AI system can do, but also how information entered into that system is stored, processed, protected, and shared. Closed systems, depending on how they are designed and deployed, may provide organizations with greater control over these issues. But closed-source AI also has limitations. The first limitation is narrow knowledge. A system designed around carefully controlled information may not have access to the broader range of information available through more open approaches. This limits the data available to the AI system upon which it may draw conclusions. The second limitation is reduced flexibility. If the AI system has been designed for a specific purpose, users may have limited ability to modify it for new situations. For example, an AI algorithm designed to predict infrastructure damage may not be able to include a casualty prediction as well. And third, closed systems require continual updates. Emergency management is constantly changing. Hazard maps change, infrastructure changes, populations change, emergency plans change, technology changes, policies change. A system that relies on trusted information is only useful if that information remains current. A highly accurate database from 5 years ago may be considerably less valuable during today's disaster. An analysis of these two source types begs the question, which source type is better? The answer depends on the mission. The emphasis should be on choosing the appropriate model based largely on whether flexibility or accuracy and control are the greater priorities. Open approaches may be useful when emergency managers need exploration, creativity, customization, broad information gathering, or rapidly changing information. Conversely, more controlled or closed systems may be preferable when the mission requires trusted data, security, repeatability, and consistent results. The important lesson is that emergency managers should not choose technology simply because it is the newest or most sophisticated option. Questions they should ask include, what problem are we trying to solve? How reliable must the information be? How quickly does the information change? And what are the consequences if the AI produces an incorrect answer? Those questions become especially important when we examine how AI can be incorporated into the 4 phases of emergency management. Let us begin with mitigation. Mitigation involves actions taken to reduce or eliminate long-term disaster risk. AI can support mitigation through hazard prediction, flood mapping, wildfire forecasting, and infrastructure analysis. For example, AI systems can analyze large amounts of environmental and historical data to identify locations with elevated disaster risk. Flood risk models can combine rainfall information, elevation, drainage systems, development patterns, and historical flooding. Wildfire models can examine vegetation, drought conditions, wind, temperature, terrain, and previous fire behavior. AI can also assist with infrastructure analysis. Transportation systems, bridges, electrical networks, water systems, hospitals, and communications infrastructure can be evaluated to identify potential vulnerabilities. The objective is straightforward. Use information before the disaster to reduce consequences during the disaster. The second phase is preparedness. Preparedness involves developing the capabilities necessary to respond effectively when emergencies occur. AI can assist with planning, training, scenario development, and resource prediction. Consider emergency planning. AI systems can help planners analyze large emergency operations plans, identify potential gaps, compare planning assumptions, and develop scenarios for exercises. AI can also help create realistic training situations. Imagine telling an AI system, develop a scenario involving a Category 4 hurricane making landfall near a metropolitan area, causing widespread power outages, hospital evacuations, transportation disruptions, and cellular network failures. Within seconds, AI can help generate a scenario that instructors can refine for a tabletop exercise. AI can also support resource prediction. Based on historical disaster information, population characteristics, hazard exposure, and projected conditions, AI may help estimate how many shelters, emergency personnel, vehicles, generators, medical supplies, or other resources could be required. Again, AI does not replace the emergency manager. It expands the emergency manager's ability to analyze possibilities. The third phase is response, and this may be where AI's speed becomes especially valuable. During disaster response, emergency managers operate under intense time pressure. Information arrives constantly. Decisions must be made quickly. AI can assist with resource allocation, GIS mapping, crisis communication, social media monitoring, and damage assessment. Suppose a hurricane has just passed through a region. Emergency managers may receive thousands of pieces of information from emergency calls, field responders, weather systems, hospitals, utility companies, social media, drones, and satellite imagery. No individual could manually analyze all of that information immediately. AI can help organize and prioritize it. AI integrated with geographic information systems can help identify damaged areas and visualize where resources may be needed. AI can also support social media monitoring by identifying emerging reports of flooding, trapped residents, infrastructure damage, or other problems. But do not forget about misinformation. A social media post claiming that a bridge has collapsed does not automatically mean that the bridge has collapsed. AI may identify the report. Humans still need to verify it. Another important application involves damage assessment. Satellite imagery, aerial imagery, drones, and deep learning systems can help compare conditions before and after disasters. Instead of requiring teams to manually inspect thousands of images, AI can help identify areas showing possible structural damage, flooding, debris, or other impacts. That information can then help emergency managers prioritize field assessments and allocate resources. The final phase is recovery. Recovery can continue for months or even years after a major disaster. AI can support recovery through damage mapping, infrastructure restoration, FEMA documentation, and recovery prioritization. Consider a community where hundreds of buildings, roads, utilities, and public facilities have been damaged. Government officials must determine what happened, document damages, estimate costs, prioritize repairs, and coordinate assistance. AI can help organize damage information and identify patterns across large data sets. Damage maps can show concentrations of severe impacts. Infrastructure information can help officials determine which repairs should receive priority. AI tools can also assist agencies with organizing the enormous amount of documentation associated with disaster recovery and federal assistance programs. However, AI should support, not replace, professional review. Recovery decisions affect communities, public funds, infrastructure, and people's lives. Human oversight remains essential. In summary, first, there are two different source types of AI: open and closed. Open source AI uses data from publicly available sources. This generally results in a greater amount of data upon which the AI system may work. Conversely, closed source AI uses systems and data that is carefully controlled by an organization and is not generally available to the public or other organizations. There are important differences between open and closed approaches to artificial intelligence. Open approaches can provide flexibility, customization, broad information access, and opportunities for innovation, but they may also introduce concerns involving hallucinations, misinformation, and inconsistent reliability. Closed or more controlled approaches may emphasize trusted information, accuracy, security, and consistency, but they can also have narrower knowledge, reduced flexibility, and a continual need for updated information. Neither approach is automatically appropriate for every emergency management mission. The correct question is not, which AI system is best? The better question is, which AI system is appropriate for this particular task? Second, artificial intelligence has potential applications throughout the entire emergency management cycle. During mitigation, AI can help predict hazards and identify vulnerabilities. During preparedness, it can support planning, training, scenarios, and resource forecasting. During response, it can help analyze information, allocate resources, monitor changing conditions, map impacts, and assess damage. And during recovery, AI can assist with damage mapping, infrastructure restoration, documentation, and prioritizing recovery activities. Perhaps the most important lesson is this: artificial intelligence should be viewed as a decision support capability, not as a replacement for emergency management professionals. AI can process information faster than humans. It can recognize patterns across enormous data sets. It can help predict what might happen, and it can help emergency managers identify options. But emergency managers must still evaluate those options, verify critical information, understand the community, consider ethical and legal consequences, and ultimately make decisions. As AI becomes increasingly integrated into emergency management, the most successful organizations will probably not be those that simply adopt the most AI. They will be the organizations that understand when to use AI, which type of AI to use, how to verify its outputs, and when human judgment must remain in control. Thanks for watching.